Hello and very good. Let's wait for some time for then we'll start. Okay, so I welcome you all. Session 3 is current. So, what we will discuss assignment sections, and then we continue tips and all this topics taught. This is run by scholar uh, Kanpur. Uh, the main goal behind conduction of such sessions is to help solve the regarding content actually and solve some virtual out of said that uh, start sessions uh, discuss once we are done discussion of these questions, some of the three content. This was the first question. True strain silent in is given by. So we have discussed this concept in detail during our session. Should be a very answer for you. Like of one engineering strain. And we actually also had solved one of the questions out of this topic, finding out manually, finding out the true strain and one load in case of one discussed during the last session. Having said that, so the question actually, what is the actual order of different points in the stress strain curve? So again, we have discussed this in detail, great detail during our last class. So the strain curve, four critical points mainly, then one breaking or rupture point. So it starts with point functional limit up to which the Hooke's law followed. So up to this point, material goes back to its initial state, functionally following the Hooke's law. So, point B, uh, so elastic limit and proportional limit similar, very small differences. And so here in this particular, the elastic limit shown, that generally proportional limit. Then you have point where you have the yield, it's called as the yield stress point. There are again two uh, for yield stress points. So see, shows your, then you have point where ultimate stress point the necking starts. Ever so necking is really starting of a small neck material which actually follows up to the cracking or rupture of the material. So that is denoted. checking or rupture point. So the correct order then is option A. That you have how many represent per unit cell in case of FCC and BCC crystal structure. Again, we have discussed this in last class. Case of simple crystal, so you have one atom in overall share multiple, and then have atoms in case of structure. Similarly, additional atom at the center in case of BCC, and then addition of six different atoms in six bases of this structure. You have additional three atoms, three atomic contributions, so the it becomes question was the number present per unit cell in case of FCC and BCC. So FCC it is 4, so BCC is 2. I hope you all could have heard that. Moving ahead, question was not true. Types of manufacturing processes were shown to you casting machine forming. So casting all know process, right? Then you have machine process where happens. You have process happen. The kind of manufacturing, right? Machining is a kind of subtractive manufacturing. So okay, then you have this forming. Again, is material addition process. So addition process actually is process through which a material is shape a rock shape into that. So last option D process. Then you had a question which said that of a solid under very timed process denoted a lot of time. So stress is a kind of stress, and stress doesn't actually. So crystal structure which defines the basic arrangement ions in a solid matter actually defines solid matter. The crystal structure which defines the hardness of the matter. Crystal structure of. So van der Waals forces, you all know, include and repulsion as well as forces. So really from that they're caused by the in the fluctuating. There is a charge, so there will some of attraction or some kind of interaction between.
Hello. हेलो
Yeah, please.
सर
Please go on.
आपका आवाज बहुत कम आ रहा है सर आवाज लास्ट टाइम ही बोला था मैंने लास्ट फ्राइडे को बहुत आवाज कम है आपका
Sound is full from my side.
नहीं कम है ना इधर बहुत भी कम है मेरा भी फुल है इधर 100% है आपका आवाज ही नहीं आ रहा है
Sure, the network is fine from your side.
कम है ना सर सतीश कुमार को भी पूछो सतीश कुमार
Satish, is the volume okay in your case? I'll try to speak a little louder. I think the volume of my top as well as set to the maximum. So what does the van der Waals forces include? So course, van der Waals forces are related to the attraction as well as interactions between atoms and molecules as well as intermolecular forces. So option both A and B are correct. So in this particular CQ, you have option C is the right one. Following that, we have a question regarding toughness. Discussed resilience in the other class. So toughness, you know, actually the amount of strain energy which is being absorbed by the material before it fractures, and at the same time, resilience is something which happens only up to the elastic limit. So toughness overall, you can say, is the area on stress strain curve, the total area, the prime. So in other words, vector tough calculated as T equal absorbed and V is the volume of the material. So if modulus of toughness is asked, then you should answer that it is per unit volume. So toughness which you get out of a stress strain curve, you divide it by the volume, get the toughness per unit volume is called the of toughness. Then you have this Hooke's law. Have iterated that multiple times. Limit Hooke's law is active. So went up to it. Stress is directly proportional to strain. Limit of proportionality is what Hooke's law states. Okay. We discussed about all these different materials, real behaviors which happens in real life. So elastic materials in which the plastic deformation happens linearly with respect to application of load. This linear hardening in which there is a strain hardening process that goes plastic deformation region. You have a rigid, perfectly plastic material. Then you have Powell law in which there is a non-linear variation, stress and strain, material loading. Then you have these viscoelastic materials in which again a material actually behaves that there is a particular point from solid formation, a very thin narrow window in which the first crystals are formed. So at that point, in case of metals such as thermoplasts as well as thermosets, have one in which as a very viscous solid, and then you have material behaves as a liquid. This kind of materials are actually called as viscoelastic materials, right? So next question was about this TTT curve which we discussed the other day, temperature time transformation curve, in which the S curve actually defines uh, the different kind of the different forms of iron which are formed in the range of 910 to 0 degrees centigrade. We discussed about austenite, pearlite, and bainite, cementite in case of the iron carbon diagram. So this is only a carbon TTT curve. So austenite, bainite, and pearlite and martensite of stars, right? So the question was which metal shows which crystal structure while it shows its structure in the 910 to 1400 degrees centigrade. So this is of course talking about iron uh, iron phase diagram curve. So it is about iron metal and it shows BCC crystal structure while it shows FCC crystal structure in centigrade. Then question was about hardness. Hardness mean of simple one. All know it is the material's ability to actually resist deformation or wear. So hardness is the resistance of a material to localized plastic deformation, resistance to wear under any external. That's correct. Then in mechanism of wear happens have discussed about different kind of wears, right? So you have corrosion wear, you have adhesion wear, you have fatigue wear. All case, what happens? One particles from one of the materials in interaction will actually get dislodged, right? That occurs due to dislodging of material during sliding. Friction is a resistive force. We all know our two stages only. Each of the following form is softest and the hardest material. So your site, and because of the grain structure, discussed it, because of the very small uncrystallized crystallized grain structure, high rate quenching process, that is the hardest one. Similarly, because a very slow uh, very slow temperature reduction process, ferrite is actually the softest material of all. Amount of crystallization process. Now, which of the following basically doesn't govern transformation phases? It class. So crystal structure doesn't govern the transformation of phase. Actually governed by pressure, temperature, and time. The crystal structure is the wrong answer. It's a wrong option. So C. Shrinkage allowance. Your the shrinkage allowance which is required. There is transition from freezing temperature to room temperature of a cast, right? Shrinkage allowance actually deals with contraction of a solid casting freezing to room temperature. Although there are three types of shrinkages: solid, liquid, solidification shrinkage, out of which the shrinkage allowance actually compensates for the reduction in size that occurs during the cooling and solidification of matter. The temperature of solid phase drops from freezing to room. This is the solid shrinkage, where material is still in the solid phase, start and of end of the process. So this particular shrinkage, you need to use an allowance pattern testing. This is a very straightforward question. 6-7% carbon, you have cementite, and percent carbon, you see from that particular above. For interstitial solid solutions, solid molecules are should be very small, as their solution will be called substitutional solid, right? Okay, so interstitial, there are solid molecules which are between so the parent solution, that for that the solid molecule should be very thin, as those the interstitial sites of the solvent matrix, option A and B in this case. So gating systems, we had discussed different types of gating systems. You have top gating, bottom gating, and gating. So in this case, vertical gating is something the pouring region it is somewhere above surface of the top surface of the casting. Okay. Horizontal gating is again parting line gating. Bottom gating, you know. Top gating, you also know. So for flat casts, generally parting line gate systems are preferred. Discussed that of finds the advantages of both top and bottom, or eliminates the disadvantages to some extent. As an alloy, the mixture of two one. We discussed about solidus and liquids and solvus lines. So the solidus line temperature below which phases diagram are solid, while the liquid line defines the temperature above are complete. So that somehow summarizes the assignment questions out of both the weeks. And now actually discuss some concepts and then out of your week 3. Now, I hope you know what actually the difference is of a metal alloy. Right? Alloy is a combination of two discussed earlier. So at the temperature time graph is the metal solidifies at a particular the metal freezing of a begins and completes within a constant temperature range, whereas case of alloy, as you can see in the diagram here, there's a temperature gradient that follows. So like Ts, a range of temperature follows while metal until it gets completed. Now, uh, because of this, what happens is there are some consequences in case of uh, freezing pattern that I follows. What happens is there is a range of temperature, right? So a range of temperature means there are different dendrite formation which takes place. Because of again because of those dendritic formations, there are compositional gradient also that follows. So temperature gradient give rise to a compositional gradient also. So uh, you have different kind of grain structure that are built up. You have starting from dendritic grains, you have more columnar grains. So these varied grain sizes or grain geometry which are being formed actually gives rise to variation intensity within the particular, which is an alloy. Right? So the density variations, what happens is after a part is manufactured, gives rise to internal defects. So in the process of loading during the application phase of that, those defects actually pile up, finally lead the rupture or fracture of a particular part which was fractured. So this temperature gradient becomes the root metal behavior of the. That's the major difference. Should know one biomaterial and so let us actually look at one problem of uh, casting. There one sprue provided which has a height of 100 cross-sectional area. This is 3 square. So the cross-sectional area of the horizontal runner is also 300 millimeter square. Assume no losses. In this case, we are assuming losses will some problem losses coming slides. As of now, the question asks calculate the time to fill activity, which is having a volume of by 5 millimeter cube casting, right? And consider gravity as 10 seconds square. The very simple question. So this equation comes straightforward from continuity equations. Here E is equal to volume of the casting cavity divided by velocity. Now AG is again is called as the choke area, right? So the choke area happens to be the area which is the minimum uh, area that the flowing molten metal encounters during its path. So the molten comes to the sprue, the runner, and the gate. So The area which is the minimum one will actually govern the maximum time. So after when we are designing a sprue, when we are designing a mold process, casting process, we take care of the maximum time which will be required. So the minimum tries to the maximum time. So in this case, the area of the runner is given to the runner area 3 square. The ratio was given. Have considered the minimum area of sprue runner and gate, right? So here you just plug in the values. The volume is 3 to 10 raised to the power 5 mm cube. We take care of the units. All are given in mm here. Change. So the area is 300 mm square, and then you have velocity, which is root of twice g into h. So g is given as 10, but in meter, so you multiply by 1000 to take this into, and then uh, the height, total height is 100 mm only. At the time is 0.71 seconds. This is a sprue design problem. Diagram shown here of this tapered sprue. Uh, is put in scene surface is dotted as 1. You have the upper surface of the sprue, which is 2, then the lower surface of the sprue, which is 3. Right, so the person has a height of 60 mm, and the sprue has a height of 80 mm. The dia at the top is given as 20. You have at the bottom. Let's try it out. All right, so let's look at the solution. Expansion effect. What is an expansion effect of casting? What is casting process the mold through center sprue, right? Sprue is cylindrical. What happens is as the material flows under gravity, it gains velocity. Okay, as for the continuation, uh, the velocity increases in the course of flow. The area remains constant. So what will happen is that there is one gap between the wall of the sprue and outer surface of the flowing molten metal. So because automatically to the continuity equation and the end of the flow, velocity is more, so automatically area of the earth there becomes small. Uh, there comes one gap in the metal and the wall of the sprue. That gap actually attracts some air bubbles, and which is again leads to some of the defects because of this process, which is called as aspiration process. To encounter that problem, the sprues are generally tapered. This is how sprue in this tapered sprue, right? Just from continuation A3 by A2, just take care of area A3 by A2 is equal to V by V3, it continuation follows. Take the ratio as R, which becomes the ratio of the height. Total height, which is here 30 plus 60 is to 40, and then H2 is the height 60, right? Here, what happens? The H2 is the total H2 plus HP, the height of the pouring basin, sprue height, and HP is basin height. Height then becomes 50 plus 60 to 4. And then diameter is also given. The top is 20 mm. So we know that A3 equation, the A3 by A2 is V2 by V3 equal to R. It is square root of total height, the difference of the total height and the pole in height to the ratio, right? A3 by A2, you just plug in the form square, or you can ID by 2 square. The pi by 2 ratio gets cut off. You're left with the ratio of D3, a square of that, and it to the right hand side, which is 240 height minus of 180 height of the sprue 180. You have into 40, 3 becomes 14. Then come to a problem discusses which actually considers the frictional effect. Here a ladle is shown, a height of 1.5 meters, and one nozzle outlet on 100 millimeters of dia. Okay, so the ladle is filled LSI alloy at 700 degrees centigrade. Time required empty the ladle if it's filled LSI alloy at 740 centigrade. Again, you have to find the discharge rate. This particular nozzle kg per second cases. First one, if the ladle is full. The second one, ladle is half empty. Okay, it's a half filled. Let's try out this question. Given here two parameters which you may need, one density to 700 per meter, is viscosity, which is 0.0273 kg per second. Try to solve this problem. consider the frictional effect in this case. So we didn't losses in the earlier problem. Here we will consider frictional losses. If you are able to do this problem, able to solve most of the questions out of assignments, concepts will be. Let's try it out. I hope you have some idea of solve this kind of problems. I solution. This is the ladle having a eye of nozzle of 5 meter. So there are two questions to be answered. The the two situations when the ladle is completely secondly half filled. Find out the time of emptying the ladle as well as the discharge. Okay. So, so let at any instant the level of liquid metal be H, the variable, so it can be full, sometime it can just assume that the level of molten metal with of height H, the average velocity of the nozzle Vn CD. So we have seen in the earlier problem where we were calculating velocity simply through H. CD term has come out here because we are not considering the friction, the frictional losses. Okay, so coefficient of discharge. Now let's actually try to look at how and CD. So here you can know the mass flow discharge rate. The formula for that is given by M. So dot here represents the flow. It is the flow rate equal to rho AV. So it is the total metal, that is the density of the molecule of the area of the nozzle AN, and then the velocity metal as VL. And now, because we are considering the frictional losses, CD charge multiplied with root twice GH. G is the gravity, acceleration due to gravity, and H is the height, right? We have assumed here. Again, so this is one way to find out the mass flow rate. So find it if we consider the volume of mold in the ladle, right? So if V is the velocity, Vn is the velocity of the metal that is coming out of the nozzle. Again, we look in respect to the ladle, the reducing volume, reducing height of molten metal within the ladle, right, with respect to time, which is h dt, right, derivative of height with respect to time. That again gives the rate of reduction of molten metal within the ladle. Signify that the height is reducing, actually use this negative sign of dt, right? Just to maintain continuity, we have AL minus of AL. Dt. AL is the area of the ladle, okay? Equal to right hand side, which is the nozzle area AN velocity Vn. The density of the molten metal gets cut away from both sides. Then we have of dH dt is to the ratio of area nozzle to area of the ladle CD. Then you have of twice GH. Okay? Because it's a differential term, simply we integrated both sides here, initial HI to final height HF, and here 0 to final time PF. Through simple integrations, I find out that the total time PF time is by G L by AN square root of HI minus HF. It is the initial height HI, final height HF divided by CD, right? Charge. Up to this, if it is clear, then now proceed to see if at all frictional losses are happening. This particular, at all frictional losses are happening, then only we'll consider friction, right? Now, let us do one thing. Let us first take CD as 1. Let's assume CD as 1 here in the Vn equation, where if CD becomes 1, it becomes simply Vn GH, which was the case in previous problem. Frictional losses were not considered. So the nozzle velocity in that case simply becomes 5.42 milliseconds. You just plug in the values G and H, right? And then the total height 1.5. Simply get the velocity of the nozzle is 5.4. check the Reynolds number. It is rho VD by mu, viscosity value which was provided to you. City of the molten, it is 5.42 is the nozzle velocity we have found out now, and this is the characteristic length dia is given as 100 millimeters. So it is 0.1. See that this number actually comes out to be 5.36 10 raised to the power 5. So this is the turbulent regime. What actually are the Reynolds number? The laminar regime, it is up to 4,000. Okay, and beyond that, 10 to the power 5 or 6, we can set that as turbulent regime. So if you have looked at tree content, so you know that beta is one coefficient which actually determines the velocity distribution. So, so beta is 1 in case of turbulent regime. So and then there is one coefficient EF which actually uh, influences the friction factor F. So EF again is varies for different kind of geometries or inlet areas. So in case of a tapered geometry, so we have a tapered geometry here, right? So is tapering out pedal towards the outlet. So tapered geometry, EF again gets modified as 1/6 actually. You can find it out from this kind of demonstrations. This data will be provided to you. I don't. So there are different situations. There can be different situations such as straight entry, projected pipe entry. There can be entry with a rounded corner. There can be entry with a tapered corner. So in our case, it is a tapered corner. Right? So in tapered corner, the factor EF, which actually influences the friction, is modified of the actual EF. Then from that, this formulation comes, and then you have the actual EF as 0.45. Again, if you look at this curve, this plot, sudden contraction, so you can this has been experimentally obtained. Okay? So the plot between EF on the y-axis and the ratio of A2 by A1, in A2 here actually represents the ladle area, right? A1 is the nozzle area. This one is the ladle area. This is the nozzle area. So the ratio of that ladle to nozzle with EF, we get this kind of curves, and then again for different kind of regime. So these are laminar flows, 0.05 RE, then this kind of curves. Again, turbulent regime, you have 30,000, right? 10,000. In our case, I have checked our number is coming the power 5 right? 36 to 10 to the power 5. So that is more than or greater than this one, so 10,000. So in anything greater than 10,000, we consider this plot only to calculate the value of. So here, if you see this plot cuts the y-axis are at around some more. Why have we taken 0.45 and why have we taken only this point is because if you look at the ratio of 2 and A1, so you can see the ladle is quite large in terms of the nozzle area. So nozzle area is only in mm and this is in meters, right? Take out the ratio nozzle area to the ladle area. You see value will be much smaller, right? Almost negligible. That case, for simplicity, the ratio has been considered as almost close to 0. That the EF here can be considered a little much more than 0.5. That's how the value of EFS comes, and that EF then 0.075. So you can see the factor influencing friction is very small, and hence again for simplification, frictional losses here can be considered negligible, right? So CD then becomes very simple. Second comes out from an equation. I think you have gone through that. Sorry, you have gone through that CD formulation, which is something uh, related to the beta value, the factor affecting velocity distribution beta, and then is inversely proportional to beta, and then addition of EF have something like 4 multiplied with friction factor F divided by multiplied by L by D, right? And the whole thing, the square rooted in the denominator, right? Now here, because the frictional losses are negligible, the terms other than this beta and EF automatically gets eliminated, right? Because F is almost zero here, then the CD becomes very simple. This is the ratio of uh, 1 to square root of 1 plus 0.075, the EF value. It's coming out to be 96. Now, I hope you got it. Just try to process, and then we'll actually process it. All right. I hope you got this to this point. So, how we actually found out CD to be 96 one using those graphs for the entry points as well as uh, the EF values. Okay. Let's take another case in which regime could be a laminar case, right? We're just trying out different cases. Of course, our case in our problem is 5.36 into 10 raised to the power 5. So we are now trying out different regimes to see how the CD actually varies, right? So in laminar case, let's consider REB 0, right? So the beta in this case becomes half standard values. F here becomes zero point 0.2. Same way we have calculated F in the other case in the turbulent regime. Okay. So now you can see in the laminar region here close to 0. So let's take up the first line somewhere between 1 to 1. When you divide it by the entry condition, that is 1/6 of that, you some the value somewhat like 0.82. Then you find CD again by beta, and this was the equation which I was mentioning in the earlier case. 1 by beta plus EF plus 4 times friction factor F L by D plus L equivalent whole to the power minus of half. So this whole thing gets cut off because the friction losses are found zero, almost negligible, so zero. Then you have the CD as 2 plus 0.82 to the power minus of half, it's coming out 69. Now the CD in that case was almost close to 1 in case of turbulent regime, but in case of laminar regime, you can see the CD is coming quite a significant value. It is 0.69. Similarly, let us consider one more case, which is somewhat intermediate. Okay, where again let us take the height h equal to 0.05 meter and take any height here. Just want to check at an intermediate position. Assume CD equal to 1 again. So you can find out the nominal velocity as power of twice of g into 0.05. It is coming almost equal to 1 meter per second. Then you find the Reynolds number the same way. It is coming out somewhere around 98,000. Okay, which is again in the turbulent region. So you take beta equal to 1 and find EF as 1.6 of EFS, which is zero point 0.5. I've seen that from the graph earlier. So the seen it for turbulent regime, and it is greater than 10,000, and the ratio to YA1, the ratio of nozzle to ladle area very small, close to zero. We find that the EF value comes out somewhere around 0.45. This follows here again 1075 is the EF value. So the CD calculated using the same process we found turbulent regime. It is coming around 96, right? So uh, this is how you check it for the different regimes of flow. So you have done that, you find out. So our problem is in the turbulent regime only, right? So the CD we can now consider as 0.96, and hence the total ladle area. Then calculate pi square by 4. D is 1 meter. It was given. Check. So D is 1 meter, right? Of the meter. So D is 1 meter. Find out the area of ladle as 0.785 meters square. Similarly, area of the nozzle is 100 millimeters. It comes out to 0.1 meter here. It again comes out to 7.85 into 10 to the power minus 3 meters square. So then comes the total filling time, TF, as the of equation which we derived, right, through the integration. So it's square root of by g. multiplied by area of ladle to area of nozzle by 1 by point of 96, which is actually the CD, um, multiplied by square root of the time height reach, which is 1.5. Okay. So it is somehow comes out to 57.6 seconds. Okay. Then you have to find out the discharge, the rate of mass flow of molten metal through the nozzle. Again, rho AV, the rho is the density of the molten metal, which is 700 kg per meter cube. This area of the nozzle, AN, 7.85 10 to the 3. Then you have CD, that is root twice, or twice GH, 1.5 the height. And you find mass flow rate is 98.73 kg per second. Okay. So tried out three cases just to confirm that our problem, how does the CD varies with different regimes, just as a part of demonstration. Then found out that in our problem, which is in the turbulent regime, the CD remains close to 0.96. Okay. Tried out in the extreme turbulent regime, as well as it tried out somewhere intermediate case. Okay. Taking H somewhere between 0 to 1.5, it is 0.05. So that's way that we have found out the filling or emptying time as well as the mass flow rate through the nozzle when the ladle is full. Okay, we have considered here the full height, no, 1.5. Same way, can you try to find out the mole fill time and the mass flow rate when the ladle is almost half, okay, half full with the molten metal. So it will follow the same problem and the same flow of operations, and just show you the solution in a little while. Okay, let's try it out once. So let us proceed with the other case which was asked in this problem, was to calculate the filling or emptying time as well as the mass flow rate when the ladle shown in the problem was half empty, or say half filled with the molten metal. So when it is 50% empty, the height becomes half of the height, which is 1.5. It is 0.75, and then mass flow rate then becomes V, is the density of the molten metal, and 7.85 into 10 to the power 3 is actually the area of the nozzle. We have calculated it earlier in this case. So then you have the total velocity of discharge through the nozzle, which is CD power of twice GH. Now the H in this case becomes half simply, and CD is 9.96 for a turbulent regime flow. Total mass flow rate becomes 69.81 kg per second. So I hope the problem clear now. The problem, this is a lengthy problem, but in a way uh, it happens to clarify a lot of concepts during feeling regarding the mode problems which you may find, okay, be uh, in the problems where frictional losses are not considered, and also in the problems where frictional losses are considered. Okay. So the catch here is to check out how is the CD varying, right? Just consider CD1 here to see cross check if CD value is in the turbulent regime, if at all there are frictional losses, okay, in the turbulent regime. So we found out that RE value is in the range of 10 to the power 5. We used to found out the coefficients which are related to the flow in case of turbulent regime, and then we found out that the frictional losses are negligible, right? So CD was again close to 1. Right, so we checked out the laminar case in which we correctly found out the CD as 0.69, and then we looked at another or the third case where we consider an intermediate case, more than laminar, less than the extreme end of turbulent regime, and then we consider the height as 0.05, and here also we found out the RE in the turbulent regime only. We found out the CD pairing as 0.96 again. So it confirmed that our flow is in the turbulent regime and CD varies as 0.96. Okay. Then we use that particular CD to find out the mode filling time and the mass flow rate through the equation, which was either you can remember, or I don't recommend remembering such equations. You can just equate the uh, like this equation. So you can just equate the flow rate out of the ladle and again out of the nozzle, which must be equal, right? Yeah. So equating that, you find out the total filling time and use that equation to actually find out the total mode filling time as well as or you can say emptying time, they're equal, and mass flow rate in cases. Ladle was full and ladle was half. Okay. So having said that, I would like to, if you have any problem.
ঈদের নাম বলতে